All right, so in this next section, we are going to attempt the part twos of the January 2019 Algebra 1 Regents. I know that the part twos tend to be, part twos, threes, and fours tend to be the parts that students tend to struggle with the most. Um, Maybe those multiple choice are a little bit easier because it limits the number of possible answers, whereas the part two, it's harder to know whether you got it right or not. So we're going to go through this, try to make this a little bit easier. Try to defang the Regents a little bit. Try to make it so it's not so scary. Um, let's look at question number 25. And remember, before, like, so right now, if you've got question number 25 in front of you, what you want to do is probably pause the video right now and, like, give this a shot. Do this on your own. Do as many steps as you can on your own. Seriously, if you just copy down what I write, you're gonna learn much less than if you actually sit there and be like, oh, it's that feeling of, oh, I don't know what to do, and then trying something. It's what's like opens up pathways in your brain to find where your brain wants to store this information. If you don't first ask yourself the question of what do I know here, then you're not going to open up those pathways to your brain that is going to say, okay, this information goes in this filing cabinet here. You're going to store this in your brain where it's like note taking. Um, you want to store it in your brain in the filing cabinet up there, which you need to open up when you have it on your own the next time, right? Okay. All right, let's give it a shot. Pause it here and try your best. Whatever you can do, it's okay. Pressure's not on. All right. Hopefully you paused it and you gave it a shot. Whether you couldn't even start it or whether you got it complete. Here goes. If you got it complete, well, you can move on. If this is easy for you, you don't have to watch me do something that you already know how to do. All right. Let's see. It says solve algebraically for x. I got 3,600 plus 1.02 times x. I have this little symbol here, which hopefully we know means less than 2,000 plus 1.04 times x. Well, this problem is something really difficult here is that these numbers are large. That these numbers here are kind of decimals into the hundredths place, and then we have an inequality. But other than that, this is doable. There's nothing really scary about all this. I'm going to minus 2,000 over here, and I'm going to minus 2,000 over here. I'm going to, I could stop. Maybe I'll just stop right there. Normally, I would do the next step all at once, but for you, for those of you watching at home, I don't want to do too many steps at once. So 3,600 minus 2,000. Oops, that wasn't right. 3,600 minus 2,000 is 1,600. All right, so 1,600. And now that I see that, that seems pretty obvious. I should have seen that in my head. I didn't need my calculator for that, but heck, I'm a belt and suspenders kind of guy. Okay, now I'm going to minus 1.02. I'm going to get that on the other side. 1.02x minus 1.02x. Whoops, I didn't put my x's in here. That could mess me up if I don't copy correctly. All right, bring that down. By subtracting 1.02 from 1.02, I get 0. I essentially cancel whatever that value is. I don't know what this value is yet, but I'm going to cancel it by subtracting its equal quantity. If I subtract its equal quantity, I'm going to get 0.02, right? 0.02. If you're not sure, put that in your calculator. 1.04 minus 1.02, 0.02 x. And then some of you are like, oh, I know what to do next. And then some of you are like, well, then what do I do? Well, we have 0.02 times x. We want to get x by itself to solve algebraically for x. Therefore, we want to move this over here, and we do that by undoing the multiplication that's going on here. This is, 0.02 times x. So to get rid of it, I'm going to divide the opposite or the inverse function for multiplication, but divide by 0.02 on both sides. Divide by 0.02 on both sides. Well, 0.02 divided by 0.02 eliminates it there. So I've got x. I've got less than 1,600 divided by 0.02. That's 80,000. So I got 80,000. Now, so I got x. So how would I read this? I would say that 80,000 is less than x, or I would say x is greater than 80,000. I could switch that around if I wanted to do it one way or the other. Either way is fine, so long as you make sure that since this alligator mouth is pointing towards the x, when I rewrite it the other way, the alligator mouth has to be pointing to the x again. X is greater than 80,000. I find this one to be pretty low level on the difficulty. I suppose there's ways you could have manipulated this to. Pardon me, I'm about to cough. All right, didn't want you to hear. I didn't want to cough at you through the microphone here. I suppose there's ways you could have manipulated this equation so that you were going to divide or multiply by a negative number. And then you'd have to remember that whenever you divide or multiply by a negative number, you have to flip an inequality sign. I suppose that could be tricky. But I don't know, pretty straightforward way I manipulated it, I didn't have to do any dividing or multiplying by a negative number, so I never have to flip my sign, which I was actually kind of surprised about. I was on the lookout for like, this one's too easy. They must trying to be testing me to flip that sign. But no, I'm not going to call this super easy, but I'm hoping that now, at this point, we know to subtract, that we can, if there's 2,000 over here, and I'd like to move these numbers together, I can subtract 2,000 from 2,000 to cancel it on this side, and subtract it on this side to get this much. And I'm hoping that you can know to subtract 1.02 on both sides of the equation. There's that, addition property of equality that I can essentially add negative 1.02 to both sides of the equation, and that'll still turn out equal. This might be a little bit tricky to think about dividing by 0.02, but I'm hoping not. And then you get x is this great big number, and then the only thing you're probably wondering is, did I do it right? And you're doubting yourself whether you got it right. So pretty straightforward, I think. I'm not going to call it easy, but geez, not too hard. Not that one at least. There's some others in here that are doozies though, right? From what I recall. Let's see. Number 26. Number 26. There we go. The number of people who attended a school's last 6 basketball games increased. Increased as the team neared the state sectional games. The table below shows the data. So in game 13, there were 348 people in attendance. In game 14, it rose to 435. Game 15, okay, we see in game 18, it goes all the way to 783. Show the type of function that best fits the given data. Justify your choice of function type. Okay. Well, what options do we have here? We have linear. We could have exponential. We could have quadratic. But is it going up and then going down? I don't. Maybe we could. Maybe we're just seeing part of the local area of a quadratic function, but probably not. Probably not. Probably not a square root function. Although let's keep that one in mind. Now, an absolute value function. Let's assume it's either linear or exponential, just for the moment, and see how we do. Now, why would I limit my options to linear or exponential? Well, when things are increasing, generally on the Algebra 1, we're either talking about a linear or an exponential function. Those are two of the general we're talking about. It can get tricky, but there's other options. Let's see about this. Let me test to see if it's exponential. Let's see. If it's exponential, then I should see the same multiplier between my intervals. So say 435 divided by 348 should be the same as 335 divided by 348 should be, no, I don't want minus, I want to divide. Should be, okay, I got 1.25, okay, fine. 522 divided by 435. I got 1.2. Oh, okay, that's maybe. 609 divided by 522, I get 1.16. This is not looking very exponentially at this point. Let me try 6.96 divided by 609. Yeah, it keeps, it's not, I have a, at first the multiplier was 1.25. Okay, that could be a multiplier. Went to 1.2 and I'm like, okay, that's not too far away. Maybe it's still going to stay in the same neighborhood, but I can see the multiplier is going down. So at this point, I'm like, exponential is not really fitting this function too much. Let me test the linear function. I think this is a linear function, which is why I tested the exponential function first, so you could see what that looks like. Instead of dividing, this time I'm going to start subtracting. Okay, 435 minus 348, that's 87. Okay, 522 minus 435, oh, that's 87. Oh, that's pretty good evidence right now that we're at a linear function. 609 minus 522, oh, that's, oh, yeah. 696 minus 609. I'm guessing this is going to be 87. Oh, there it is again. And 783 minus 696, 87. Okay, this thing is solidly a linear function. So let's go back. We know what we know now. Oh, I should explain why we know it's a linear function. All right. When I went from 435 to 348, I found out the difference was 87. I went up 87 from here to here. I went up 87 again to go here. Up 87, up 87, up 87. Because I'm going up 87 each time, I know what I have is a constant rate of change. And when I think about constant rates of change going up by the same amount for every interval of x, I want to think linear function. That's a straight line, right? Oh, I got my pencil. Straight line, right? So I got a straight line. I'm going up at a constant rate of change. It's not changing because it's a straight line. Constant rate of change is a linear function, a straight line. So, state the type of function. Easy peasy. Linear. That best fits the given data. Justify the choice of function type. Okay. Well, here's where I have to show them my evidence, right? So I'm going to say 435 minus 348 equals 87. I'm going to say 522 minus 435 equals 87. 609. I don't know where that zero came from. 609. 609 minus 696 equals 87, right? And 6. I don't even know if all this is necessary. 696 minus 609 equals 87, and 783 minus 696 equals 87. And I'm going to say this is a there is a constant rate of change. Therefore, a linear function has the best. All right? Can you read all that? There's a constant rate of change. Therefore, a linear function has the best fit. And I'm showing the math of constant rate of change. Pretty straightforward. Gosh, I want to call this one in the medium range. That wasn't too bad. You know, once you start playing with your output values and you recognize that there's a constant rate of change, hopefully by now, when you think constant rate of change, you think linear function. So hopefully that's pretty easy to identify that it's linear. And of course, you know, it's pretty easy to tell them why. The only hard part of this, I guess, would be the statement at the end, would be to say something about the justification, the why. Justify your choice of function type. You'd have to kind of remember that special vocab term of constant rate of change or something similar. You could say, okay, I could say, because the output is going up at a constant rate, therefore linear function is the best fit, or because the y value or output are going up the same amount each interval of x, therefore linear function has the best fit. All of those works. All of those works. You're just basically using the same definition as a constant rate of change. All right. Okay. Number 27. Okay. 27 says solve algebraically, and I see a quadratic. Already, I'm going to say this isn't. I don't know. I know this isn't too bad for me, but I know it's a lot of students. They struggle with factoring quadratics. Now, as I look at this, I think this one's easy to factor too. But if you haven't spent enough time factoring, if it's not a skill you're good at, it's going to be difficult. Okay. So x squared minus 8x minus 9 equals. I am going to try factoring this right away. Now, I could do the, it does solve algebraically. So I could go right away and I could use the quadratic formula. And the quadratic formula, I'm trying to remember if it's on the reference sheets. I do not believe the quadratic formula is on your reference sheets, but I could be mistaken. Oh, something wants to tell me it is on your reference sheet. I can't remember. But I can remember what the quadratic formula is. You could negative b plus or minus square root of b squared minus 4 times a times c, the whole thing divided by 2a. That's your quadratic formula. You don't need to write that. I don't expect you're going to use the quadratic formula on this particular problem. I'm going to factor this because that seems to be pretty easy to me. You could also complete the square if you're comfortable with that. But we haven't done a lot of that. We only did one day of quadratic formula in class because most most of you really objected that that was too much. And so I was like, okay, we can play with our between factoring and our calculators. We can get the job done most of the time with just those. With just a calculator, you can at least, if it's a funky decimal, you can at least find where it is between integers, and then that will help you find a multiple choice question. All right, so factoring. Okay, x squared. X squared tells me the only way I get x squared is for I must have multiplied x times x. That's what x squared means. It means x times x. The only way I get, two numbers that are the same number that multiply to be 25 is if I had 5 times 5 is 25, right? There's the only two numbers that are equal to themselves multiply together to be 49 are 7 and 7. Actually, take that back. There are a second set of numbers, right? There is the negative 5 option, and the negative 5 option that gives us 25, and there's the negative 7 times negative 7 option, which gives us 49. So actually, there's always two numbers that can give us a particular positive perfect square. So, must have multiplied x by x. Must have multiplied x by x. That's the only way I get x squared here. Now, we're going to ignore this middle term for just a second. We're going to talk about this term because this number times this number has to give me negative 9. Okay? Ignore the middle term for now. For the c term, negative 9. Well, I have a couple options. I could have done 1 times negative 9, or 1 times 9. That gives me a 9, which I can manipulate to make it become a negative 9 by making one of those factors negative. I could do 3 times 3, and I'm pretty much, that's where I stopped, right? Either 1 and 9 was used, or 3 times 3 was used to get me to this 9. Well, because I see I have, now I'm going to look at my middle term. Because 8 is here, I need my factors to somehow add up to negative 8 in the end. So they need to multiply to be 9, but they need to add up to be negative 8. Or they need to multiply to be negative 9, rather, and add up to be negative 8. So what I'm going to do is I'm going to choose my factors of 1 and 9. And it doesn't matter where you put the 1 and where you put the 9 right away, because we're going to play with the pluses and the minuses later, or actually in the next step. So you just put if you know the factors you want to use to get to your middle term, They have to multiply together to give you your C term. We're going to make them add up to be your middle term. All right, I'm going to make 9 negative, make 1 positive. Why did I choose to do that? Well, because I have a negative 8 here. And so by making the 9 negative, I get really, really close to my negative 8. And of course, when I add my 1, negative 9 plus 1 is going to be give me that negative 8, right? And then positive 1 times negative 9 gives me the negative 9. So let me think about this if I was factoring that. So I factored this. This is actually right. This is actually factored. I know all these things. I know that this equals 0. I know that this expression here is the same as this quadratic expression here. Therefore, this is 0. Well, if I know this times this equals 0, what do I have to multiply a number by to get 0 as an outcome? This times this gave me 0. It has to give me 0. I know this. Hopefully you're yelling. One of these has to be 0. You're right. One of them has to be 0, or both of them could be 0. Don't know. But I know at least one of them has to be. So let me assume that x plus 1 is going to be 0, or x minus 9 is going to be 0. Well, to find out what x would have to be in this case, I'm going to subtract 1, and I get x equals negative 1. Also, on this one, I have to add 9, add 9 on this side, adding 9 on both sides of my equation. I'm going to get x is equal to positive 9. So here I've solved this quadratic. I know that this quadratic function goes through the x-axis at negative 1 and positive 9. All right? If you can imagine this for a moment, let's actually use our calculators to maybe make some of this be a little bit easier. Because again, I know factoring is very hard for many of you. That's okay. You have a wonderful tool here. X squared minus 8x minus 9. Let me graph that just so you get the shape of the quadratic function. Oh, let me zoom out a little bit. What does zoom fit? See what that gets me. All right. So as you can see, this is a U shape. This is a happy smiley shape because it's a positive integer out here, positive 1. And I want to know where this function goes through my x-axis. So to do that, I'm going to go to my table. And wherever I see a 0 in the y column, whoops, what did I do? Whenever I see a 0 in the y column, that is where the function went through the x-axis. I'll say that again. Where there is a 0 in the y value in the output, that is where the function went through the x-axis, right? The x-axis is where negative and positive meet, right? The x-axis is where the y value is 0. So here I have, the y value is 0 at negative 1. Oh, calculator solved that root for me. And the y value is 0 at 9. All right, our calculator is confirming what we figured out by factoring. All right, and you could also find the y-intercept around here, right? Somewhere around here, where the x value is 0, that's where our y-intercept is. All right. So explain the first step you use to solve the given equation. So while your calculator, in this case, you could put that in your y equals, and it could find you the roots. You could write down x is negative 1, x equals 9. You're gonna, unless you can at least show them that you're factoring, you're not going to gain all the points you need for this question because it says solve algebraically, and now you need to be able to explain the first step you use to solve an equation. So if I'm going to explain the first step, I just went to the manual to confirm. If you just wrote the answer here and then also no explanation, you get no points on this question. So just using your calculator Well, a great way to check your work in this case is not enough to gain you any points on this part two. This whole thing was worth 2 points. You needed both to be able to show how you solved it algebraically with the correct answers. You needed an explanation. So um, my first step was to factor the quadratic function. My first step was to factor the quadratic function and then solve for x. And then I solve for x. It doesn't say, I don't think I have to continue the explanation. I think that's enough. Just say my first step was to factor the quadratic equation. Okay. I'm going to give that a medium difficulty overall because I know factoring is hard for many of you. And while the calculator can be a great way to check your work, and the calculator can give you the answer, the calculator by itself isn't going to give you enough to even gain a point here. But let me see if no, it doesn't look like. I was wondering if maybe if you could explain what your first step would be if you didn't know what to do, but you could explain it if that would give it to you. But it doesn't look like they had an option for that. So, all right, that's my model of how to do this one. Let's go on to number 28, right? 28. So far these part twos haven't been so bad. All right, here we go. The graph of the f of t models the height in feet that a bee is flying above the ground with respect to the time it travels in t seconds. So if I'm interpreting this, the bee starts at the ground and it goes up, and then it gets to be 1 foot above the ground, stays 1 foot above the ground for the next 4 seconds, right? 1, 2, 3, 4 seconds. And then it starts going up. It's 2 feet above the ground, going up, until it gets 4 feet above the ground at 10 seconds. And then it starts going down to 1 foot above the ground again, going back up, and then it's leveling off. State all the time intervals where the bee's rate of change is 0 feet per second. So its rate of change is 0 feet per second. What can you do with this? Try to pause here and try to think how you'd answer this. Sorry. All right. So state the interval of time. All right. I hope. Sorry, kicking the table and I'm working on. I hope that you know that the rate when the rate of change is 0 feet per second. When the rate of change is 0, you know that you're talking about a flat line. A flat line has a slope of 0, right? A flat line has a slope of 0. The rates of times when the bee's rate of change is 0 is starting here, going on to here. So all of this is a 0 rate of change, and this is not. It's increasing. This is not. It's decreasing. This is not. Oh, and then now we have another little set of where it is. The rate of change is 0, and so I'm going to say from 2 seconds. No, wait. Did it say seconds? Yes. From 2 seconds to 6 seconds, and from 14 seconds to 15 seconds, from 14 seconds to 15 seconds. Gosh, I got this one on the easy side of things. You do have to know that a flat line is a 0 rate of change, but you don't even really need interval notation or anything like that. I didn't specify. Oh, to explain my reasoning. Whoops, I'm not done. I have to explain my reasoning. I did state all the time intervals when the rate of change is 0 feet per second. Okay, so during those intervals, slope or rate of change is 0. Sorry for my messy handwriting. Trying to write fast. It always starts to turn cursive. But essentially that. During those intervals, the slope or rate of change is 0 or flat. I guess I could write flat or 0. That's my reasoning. Now I'm done. If it says explain, explain. Make sure you're not like me and just skipping over directions on these questions. All right. Yeah, I'm feeling like that one's a little bit on the easy side of things. There's hardly anything to calculate there. There's just reading a graph, and we did lots and lots of interpreting graphs and equivalent representations, interpreting tables, interpreting function rules. Okay, so I'm hoping that's a good one for you. All right, let's move on. Daisy. This is our last part two. I think we still have some more to do. More part twos to do. Okay. Graph the function f of x equals 2x minus 7 on the set of axes below. Okay. Yeah, I could do that on paper, but we have this wonderful tool that will help us out with this. So 2. Oh, I want to make sure you see every button push I'm doing. Okay, clearing it out. Starting from the beginning. You can see all my button pushes. 2. Raised to the power of, so I'm pressing the caret button, it's that arrow button again. Raised to the power of x. X is this button right here. Right, that's the way I insert a variable in my calculator. Minus 7. Minus 7. Once I've got that, I can press second and press the graph button, which is really I'm going to the table. Right, if I press the blue second button first and press the button that's labeled as graph, it's also labeled as table in blue, I go to a table. Now the table is wonderful because now I have to do a lot less work. All right, sorry. Slight interruption there. Okay. So, as I was saying, my calculator can be of a great help here. I'm going to go to, let me see. I'm going to go where the numbers start being something I can interpret. Negative 2, I'm at negative 6.75. So at negative 2, I'm at negative 6.75. So here. At negative 1, my calculator says I'm at negative 6.5. So here. At my calculator over. At 0, I'm at negative 6. Okay. At 2, I'm at negative 5. At 1, I'm at negative 5. At 2, I'm at negative 3. At 3, I'm at 1. At 3, I'm at 1. At 4, I'm at 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3, I'm at 1. Okay. I can now begin to graph this line. All right. Graph the function on the set of axes below. Done. We have graphed this function. Now, hopefully, when you saw that it was 2 to the x power, you knew this was going to be an exponential function. You knew that it was going to be doubling every time. So if I start here, I go from 0 to, I'm going 1, and I'm going up 2, and I'm going up 4, and now I'm going up 8, right? It's because I'm multiplying by 2 for every interval of x. If it's negative 7, you knew that means it dropped this function down to negative 7, where it would normally be as a parent function of 2 to the x power. And then they're going to give me a little bit extra to this question. If the g of x equals 1.5 times x minus 3, determine if the f of x is greater than the g of x when x equals 4. Okay, well, I've already got this one function in here. Let me add the g of x in there as well. 1.5. Oh, you can't see. 1.5 times x. 1.5 times x minus 3. Well, this is going to be a straight line, right? This is going to be a linear function. Oh, and okay, well, All right, so as we can see, all right, hopefully as you can see, if I don't, there we go, that this linear function crosses somewhere around here. They want to know which function is bigger when x is 4. When x is 4. So I'm going to go to my table. I'm going to go to where x is 4. Oh, and then I see here, oh, moving things around. When x is 4, this function is way up here where y is 9. But where x is 4, the other function is down here at 3. So where x is 4, this other linear function is at 3. So let me just, I don't have to graph this other function. I'll graph it for you. Negative 3, 0. All right, didn't have to graph this, just graphing it for the folks at home. All right. As you can see, at 4, our original f of x is greater. So I would explain this. I would say the f of x is greater with a value of 9, with a y value of 9, when, why am I doing, sorry, I'm thinking ahead of myself. When x is equal to 4, then the g of x with a y value of, what do we say, 3? With a y value of 3 when x equals 4. All right, I don't even know if I needed all that. I probably could have said something similar to that. The f of x is greater because it has a y value of 9 when x is 4, while g of x has a y value of 3. I don't know. You need something about the y values of f of x are greater than the y values of the g of x, or the output of g of x when x equals 4. That's what your explanation is. Your explanation is that it's down here. This function is down here, while this function is up here. X is 4. All right. Moving on, keeping on. All right, determine algebraically the zeros of the f of x. Ooh, this is a quadratic. That is substantial. This is a substantial quadratic. Why is it substantial? Because it's got a 3 out in front here. Well, I think this is factorable. I think this is factorable. I'm going to go ahead and try to factor it. But you might want to use the quadratic function if you're so inclined. You might. I'm thinking this is factorable. 3x. Oh, wait. X to the third. Ooh, wait a minute. There's an additional wrinkle. There is an additional wrinkle. I didn't realize when I first looked at this. Oh, this is not a quadratic. This is a cubic function, right? We got x to the third over here. I'm going to need to reduce this to something I can manage. So what I'm going to do is I'm going to take an x out of the whole thing. And divide this by, I don't know if dividing by x is the right way to show you. Let me just factor an x out. Let me do this, because I don't want you to think that I can just magically make everything go away by dividing by x. In my head, that's what it works, how it works. But that's not the best way to show you. So I'm going to pull an x out of each term in this expression. So this becomes now 3x to the second. This now becomes 21x. And this becomes just plain old 36. Do we see how that works? I'm factoring the x out. X is still there. It hasn't magically gone away. I'm factoring it out now over here. So x times 3x squared would be 3x cubed. X times 21x would give me 21x squared. And x times 36 give me 36x. These are equivalent expressions. I just pulled the x out. And now I can try to factor the quadratic function. But again, I can't forget that x is out there somewhere. All right. Now, the nice thing is that there aren't many factors of 3. The only options I really have to get 3 are 1 times 3. So I put a 3 here, 1 here, because my only real options are 1 and 3 for this. All right, now I have to think. Oof, this is the hard part. And I'm gonna rate this as a hard question. This is a hard question, okay? We sometimes get hard questions. I need to think about the factors of 36, and there's a lot of them. The factors of 36. When I multiply one of them by 3, I can get everything to add up to be 21. Okay, this puts a wrinkle. This is not an easy factoring job. Let me think about this. Factors of 36. I'm just going to brainstorm some stuff out here. 1 and 36. 1 and 36 works. 2 and 18. That works. 3 and 12. 4 and 9. Man, that's a lot of options to play with. So let me think. 1 and 36, I don't think is going to work in any way, shape, or form. 3 times 36, that's puts me way outside the ballpark. 36 plus or minus 3 times 1 gives me 33 or 39. That's not the 21 I'm looking for. So I'm rejecting those. I'm rejecting this factor. Let's see. 18 times 3, that went way out of the ballpark. 18 plus 2 times 3 is 6. Is 18 plus 6 21? No. That's really not going to work. I'm going to reject this factor pair out there. Let me see about this one. 12 times 3 is going to be 36, right? Minus 3, will that give me? No. That's not going to work. What about 12 plus 9? Well, 12 plus, wait a minute, 12 plus 9? That gets me to 21, right? So this is a possibility. That's a possibility. 4 times 3 is 12. This is also 12 plus 9. This is a possibility. Let me play around with these two. Get 21. 3 times, all right. I paused it for a minute to kind of consider what the best way to show this up to you. I realized that, okay, I could actually have 2 factors that work. Why do I have 2 factors that work? Because I didn't completely factor this right from the beginning. I just assumed this was a hard problem. I didn't think I could pull a 3 out of this whole thing from the very beginning. So we could do this. We can do I can put a 3 here. I can put a 12 here. I can put an X. I can make that plus. I can make that plus. And then eventually, hopefully, I would see to pull the 3 out here. Or I could then eventually say, okay, well, if this equals 0, if this equals 0, or when this is 0, then what would X have to be to make this times this 0? Well, then I'd have to have X. You can't see what I'm writing. X has to be 0 because I have an X out in front. Well, what if 3x plus 12? When is that 0? Well, it's when you minus 12 here, when you minus 12 here, which gives you 3x minus 12, and divide by 3, I get x equals negative 4. So I get x equals 0, x equals negative 4, and when is 1x plus 3 going to be equal to 0? Well, I minus 3, I get x equals negative 3. So it all works out. I mean, it all works out, but maybe a better way to think about this, because I'm basically made it unnecessarily hard to factor. Essentially is what I did. I'm going to say this is the same as 3x, and I'm going to pull, just like I pulled an x out of this piece, I'm going to pull 3 out of each one of these numbers, because I'm going to see that there's a greatest common factor here. If I pull a 3x out of here, I just get x to the second. If I pull a 3x out of plus 21, I get just 7x. And if I pull a 3x out of 36, I'm going to get 12. And now maybe this is easier for you to factor. Maybe you're going to say to yourself, oh, well, 36x x squared plus 7x plus 12. Maybe I can factor that one a little bit more simply. I'm going to have x. What factors of 12 will give me 7? Well, 1 and 12 aren't going to work. 2 and 6. 2 and 6 will give me 8. That's not going to work. 3 and 4. 3 and oh yeah, 3 and 4 add right to 7. 3 and 4. And then hopefully they both be positive, both be positive. Then you're going to see that x is going to equal negative 3. X is going to equal negative 4. And you're going to get the answer that way. And of course, x has got to be 0 for that to work. So you're going to get it that way. This I feel is more straightforward. I feel like when I first saw this, the difficulty level I thought was really super high. Now I'm going to say it's still difficult, but it's, the difficulty level in my head is lowered. But still, not an easy problem. Not an easy problem. Did I solve everything? Yeah, that's just determined algebraically the zeros. There's no explanations needed. Once you get it a quadratic like this, once you get it to a quadratic like this, you could go to your calculator. You could go to y equals. And you could put this quadratic in your calculator. You can go to the table. Then you can go and confirm for yourself, when is my y 0? Oh, look at that. My y's are 0 at negative 3 and negative 4, if you can see that. So you can kind of confirm your answer and you can get them, but remember you need to solve algebraically, means to like show them your work, to show them what you've done to get there. And for that, you're going to need the old noggin. You're going to need to know how to factor. So while the calculator is great for checking, it's great for multiple choice questions. It's part 2s and part 3s. You're going to need to either know how to factor, or you're going to need to know how to complete the square, or use the quadratic formula. Your choice, whatever works for you. Factoring often gets the job done. Number 31. Santina is considering a vacation and has obtained a high temperature data from the last 2 weeks from Miami and Los Angeles. So it looks like which location has the least variability in temperatures? Explain how you arrived at your answer. Okay, gosh. For me, I'm going to have to rate this one to be a hard one because I skipped over a statistics unit because we were just doing a half year of Algebra 1 review. We didn't have that full year to kind of go more in depth. So you're going to have to kind of use your understanding of what variability means to figure this one out. What does variability mean? If temperatures vary, what does that mean? If you ever heard your results may vary, what does that mean? It means variance is a change, right? If your results may vary, it means your results may be different from what I'm showing you. If temperatures vary, it means that you can have really cold temperatures and really hot temperatures. What would be something that has low variance? Well, if it stays hot all the time, very low variance. If it stays cold all the time, very low variance. If the temperature is wildly going up and down, that's a lot of variance. So let's see if we can see where there is a lot of up and down. I went from 76 in Miami to 75. It goes down 1. I went up 8, right? Went up 8. Then I went down 10. Then I went down 13, up 6, up 10. Okay, from there to there, I went up 5, right? 5, and then down 2, up 2, down 2. Let's see what else. So I'm going. I feel like Miami's got some ups and downs there. Are they any worse than Los Angeles? Went from 74 to 63. Went down by 9. Went up by 2, up by 2, down by 2. Stayed the same. Stayed the same. Went down 3. Stayed the same. Went up 10. Okay, that's a big variance. And then down 4. Okay. Down 5. Okay. Stayed the same. Went down 3. What do you think from what we just did? It seemed to me like Miami went up and down a whole lot more. So Miami would have the greatest amount of variance because it went up and down quite substantially over the course of this data. While in Los Angeles, we had a lot of days of stays the same, stays the same. So the question asks, which location has the least variability in temperature? The one that has the least variability in temperature is Los Angeles. All right, Los Angeles, because its temperatures did not change as much day to day. You could say because its temperatures did not vary as much from day to day, because its temperatures were not so did not have so much drastic variability. Were not so erratic. There's all sorts of words you could use. I am going to call this one hard because I skipped over the statistics unit and didn't really specifically talk about this kind of question before. Um, but if you know what variability means, if you got a, if you knew that, you can kind of make sense of this and piece this together, pick up some points. If you can at least identify that Los Angeles is going up and down a lot less, a lot more even keel than Miami, which is a little more erratic, going up and down more drastically. You can kind of answer this one with just knowing what variability is and then looking at the differences and kind of plotting them out. Another thing you could do, this is a great time to get graph paper, right? If you were to take a scrap sheet of graph paper and you were to plot these two functions out as they go up and down, then you could see that Miami has a lot of this, and you would see that Los Angeles has a little bit more like this, and then you would know that Los Angeles has the lesser variability, right? There's also a way to use the stat button on your calculator, and then to enter all this data in there, and then run like statistical models on the data you've inputted it. But I haven't shown you that. I'm not going to show it to you here. We'll get into that in a statistics unit in Algebra 2, or when you see me, we'll try another time. The statistics unit. I think there might even be some statistics in geometry somewhere. I'll have to look at those standards again. All right. Last part two. I'm going to wrap up this video. Last part question. Solve the quadratic equation below for the exact value of x. All right. Pause here and see what you can do. Just what you got. All right. Hopefully you paused the video and now you've got some work down and you tried something. You put it in your calculator, right? You knew you could do that, right? You tried to factor this, right? No? Try? All right, hopefully you did. All right, well, solve this quadratic function. I'm going to subtract 75 on this side. I'll subtract 75 on this side. Why am I doing that? Because I want my quadratic function to be equal to 0, so I can see all of its parts. I get 4x squared minus 80 equals 0. Okay. My next step is I want to pull a 4 out of this. I want to simplify this for myself a little bit more. Okay, so now I have 4 times the expression x squared minus 20 equals 0. All right, what can we do from here? Well, all right, now I'm going to try to factor this expression right here. I have, now the thing is that to get x squared, I got to have an x times x. What number will multiply by itself will give me 20? Because, 4 times 4 is 16, 5 times 5 is 25. There's no really good integer number that works here. But there is a number. There still is a number. It's just called square root of 20. Now, if you put the square root of 20 in your calculator, you're going to get an irrational number, all right? Square root 20. You're going to get this big, long decimal, which is kind of a pain in the butt to work with. But if we keep it in this form of square root of 20, we don't have to, we can just keep it this way. We don't have to change anything. Now, well, I just put, I'm not even thinking about it, I put a plus here and a minus here. Do you know why I did that? Because I have a negative here, right? I need two numbers that when I multiply them together give me a negative 20. Well, the square root of 20, the square root of positive 20 times the square root of negative 20, or negative 1 times square root of 20 will give me 20. Now, let's confirm this in our calculator. The square root of 20 times, nope, that's not what I wanted. 20 outside the square root times the negative, whoopsie daisy. I'm going to put negative 1, second 20. All right. Do you see what happened just now? When I took the square root of 20 and I multiplied it by the negative, square root of 20 times negative 1, I get negative 20. Why? Well, think about this. 5 times 5 is 25. The square root of 25 is 5. Therefore, I could say if 5 times 5 is 25, and if 5 equals the square root of 25, therefore, the square root of 25 times the square root of 25 is going to give me plain old 25. See how that works? So the square root of 20 times the square root of 20. I know it's a big ugly number that I don't want to deal with. But I know that together it's going to give me 20 when I multiply them together. I want it to be negative 20, so I made one of these negative. And just like it works in every other situation here, when we have things factored like this, if x plus the square root of 20 were to equal 0, and why do I say that? Because if this times this times this equals 0, that means one of these has to be 0. Well, 4 is not equal to 0, so it has to be this or that, which is 0. One of these has to be 0. Don't know which one. So let me see what happens when this is 0. Let me see what happens when this is 0. Well, I minus the square root of 20 over here. I get minus square root of 20. X is either equal to the negative square root of 20, or I add the square root of 20 over here, add square root of 20 over here. X is equal to positive square root of 20. What's my answer solving this? Well, x is equal to plus or minus square root of 20. Make sure we can see that. All right. That's how I would get to this one. I would still just factor it and play with the square root of 20 in my head. But there are other ways. You could do completing the square. You could do the quadratic formula. You know, if you wanted to do any of those other ways, I can show you those in class as well if you're interested. I just feel that in terms of our time, effort, and energy being limited as it is, let's stick with what we know and stick with what you've learned so far. Again, like square root, quadratic formula, negative b plus or minus square root of b squared minus 4ac over 2a. I have no b term in here, so I have 0, negative 0, plus or minus the square root of, no b term, 0 squared, minus 4 times a. My a is going to be 4. All right, times c, that's going to be negative 80. All divided by 2 times my a, 4. I put this in my calculator. 0 minus, 0 times 0 is, okay, 0 squared. I probably should just put it in there the way I would want you to put it in there. All right, I get 1,280. So what is the square root of 1,280? It's this 35.77 thing. And so it's negative 0 plus or minus this number here. And it's going to be all divided by 8. And if I got this, the square root of 20, again, is that same number. Now, the problem is that if you were to do the quadratic formula this way, you would that's fine. You would just get, your answer would look like this. If you did the quadratic formula, you'd say x is equal to plus or minus 4.472135, 955. Same thing. You just don't, if you did the quadratic formula, you may not recognize that decimal is equal to the square root of 20. I find the square root of 20 way is to be a more straightforward means of doing this. Completing the square also is fine. All good things. Okay, that wraps up all the part 2s. We're now at an hour long. We'll have to do the part 3s another time. Thanks for watching. Remember, you matter. This is why we're doing this. We're going to get you there. Don't be afraid of the region. It's one step at a time. That's all we can do. Start where we're going to start where we're at, and we're just going to keep moving forward. All right? All right. Let's do this.